Okay, guys. Hello. Welcome to our first chemistry lecture with me, Mark Abdurrahmanov. Um, these lectures will just be focusing on either chemistry, physics topics that we didn't cover because they are not very high yield, or in the case of this lecture, because they're very broad and they're part of other topics and they're very basic. That's why it's called basics of bonding. And so there are things that we assume most people already know, but now that we are done with our main lectures, we're going to continue with these just in case some of you may have forgotten or need a refresher, or maybe it wasn't taught very well the first time. And these are very important, especially this lecture is very important for you to be able to understand the rest of chemistry. So we'll just go over some of this stuff. This is my personal introduction in case this is the first lecture you're seeing of me. As well, this has my name, my stats, as well as an email to get in contact with me in case you have any questions or want to set up a meeting to talk one-on-one and anything like that, okay? And feel free to reach out to me anytime with this email and I'll get back to you as soon as possible. We also have a group meet. The link will be shared with you guys where a bunch of students are part of the group chat, and as well as me and all of the other tutors. So if you ever have a question, very likely that either me, one of the other tutors, or maybe even one of the students will know the answers. So this is a great way to get your questions answered. Okay, so the learning objectives today are: what are electrons and orbitals? What are the various types of bonds and molecular structures formed by these bonds? And what are some common ions and molecules to know? So you can see these are very, very broad, very, very basic questions. Many of you probably have learned about these in some way, shape, or form 1,000 times already in your high school and college career, but we'll get started with them again, okay? First, we're going to start off with atomic structure. So firstly, starting at the very beginning with chemistry, the periodic table. All elements on the periodic table have two values on them, the atomic number and the atomic weight. So the atomic number is right up here under the name of the element, carbon, which is 6. And the atomic weight is the one here at the bottom, the 12.011. As you remember, atoms always have an equal number of protons and electrons in their standard form. And it's in quotations because this is what we call the atomic form. But you can think of the atomic form as this is like the standard form. This is the generic form that it will normally be found in. And anything other than that, like maybe an ion form, is something out of the ordinary, it's something special. Okay, and this this atomic number is it's unique to each element. So for example, for carbon, it's always 6, and it's while the electrons may be different for sometimes from this atomic number. For example, you can have carbon with 5 or 7 or more electrons, but you can never have carbon with more or less protons than 6, right? If it somehow gains a proton from something else, it gets 7 protons, and now it's no longer carbon, now it's nitrogen, right? And this is the whole principle behind like nuclear chemistry, nuclear fusion, nuclear fission. You can turn one element into another element, but so know that if you have carbon, always, without exception, it has 6 protons, right? And that's the atomic number. In addition to protons and electrons, atoms also have neutrons, which have mass but no charge. Remember, electrons have charge but no mass. At least in chemistry, in physics, they do have a mass sometimes, but in chemistry, we consider that they don't have mass because it's so small. The sum of the mass of the protons and neutrons is called the atomic weight, that 12.011 number for carbon. And a very important note, the weight shown on the periodic table for each element is the weighted average of all the masses that element can be in. So unlike with electrons and protons that have a very fixed number of protons and electrons, an atom can have a varying number of neutrons, right? So for example, even though on the periodic table, carbon has a weight of 12.01, which would make you think there's 6.01 neutrons, which by itself doesn't even make sense, right? How can you have 0.01 of a neutron? Well, it's because there's actually a 12 weight variant of carbon, a 13 weight variant of carbon, and a 14 weight variant of carbon, which This is the proper nomenclature for that. Okay, C12, C13, and C14. The weight shown on the periodic table is the weighted average based on abundance. So since 99% of all the carbon is in the C12 form, the weighted average is very close to 12. But because the 13 and 14 variants do exist, it's slightly higher than 12 because it averages, because the average, okay? And these variants, the C12, C13, C14, are called isotopes of each other. An isotope is essentially just the same atom, carbon, but with different amounts of neutrons and different atomic weights as a result. So C12, C13, C14. And in the case of carbon, it's very lopsided towards one weight. So it's pretty much almost exclusively in the 12 range. But for other atoms, like for example, chlorine, it's a lot more mixed. So I believe it's chlorine 34 and 36 are the two most abundant ones. So I think on the periodic table, it has a weight of about 35. But essentially, you don't really see chlorine 35. You see a pretty evener mix of 34 and 36, which averages out to 35. Okay. Next, I'm sure you've seen this diagram hundreds of times, is the electron atomic model, which shows the electron shells as well as the nucleus in the middle filled with protons and neutrons, right? So remember that both protons and neutrons are found in the center, like in a packed nucleus, right? Similar to the nucleus of a cell, but a little bit different. Meanwhile, electrons are found in multiple layers or shells or like rings orbiting this central nucleus, right? Then there's different layers. So for example, this first layer, then this bigger second layer, and so on and so forth. These shells have a set number of electrons they can hold. And obviously, the further away from the nucleus they are, the more electrons they can hold because the rings are bigger. So for example, this ring is kind of small. This one is bigger. Then if you add more rings, this one's a little bit bigger. This one's even bigger. And they can, obviously, the bigger the shells are, the more electrons each shell can hold. Okay. And then these are orbital configurations. Again, I'm sure you've seen many times. This is how we organize the electrons into these shells or into these orbitals, right? I have the list here of how usually the orbitals go, or the electrons get put into orbitals, the order in which they get put in. This is based on energy, which configuration is the most energetically stable and favorable and whatever. We're not going to get too deep into that because it's not as important, but just know that usually this is the case. Each atom fills the orbital shells differently due to them having different numbers of electrons, obviously. This is the general pattern, but if you really wanted, there are many exceptions. This is one part of chemistry that has a ton of exceptions. So if you really wanted to know all the exceptions, you would have to kind of learn each one independently. I wouldn't strongly encourage it because it's not that important. It's not that serious, at least for the MCAT. But if you want to be safe, and that's really the best way to know it for sure. But there are some general rules apart from this order. So usually, as you can see here, so there's the S shell, and then followed by the P shell, and then the D shell, and so on. So the S shell can hold 2 electrons, the P shell can hold 6 because it has 3 boxes, and then the D shell can hold 5 actually, like this. Then it can hold one 10 because each box holds 2, right? And each level hold you get each drawn 2 extra boxes as 1 box. Then the P shell has 3 boxes, and this is 5 boxes, right? So the general rule is usually atoms prefer to have 1 electron per box rather than start filling up the boxes any differently. So for example, we can take carbon over here. So I'm going to draw it again. So it has 2 electrons that go into this P shell because these are filled, but it only has 2 to fill this P shell, which normally has 6. So the 2 options really are 2 in the first box, and then the rest of the box is blank. Or what you see here, where each box, or the first 2 boxes have 1 each, and then the third one is blank. Usually it will prefer to do this before it does this. And you can see that again here for nitrogen. instead of filling up one fully, it actually prefers to fill them all up by one. Same thing again here with oxygen, fills up all of them, then it goes for another one, instead of maybe doubling up on one and keeping this one empty. Doesn't really like to do that, okay? So that's a general rule. Another general rule is that d orbitals are usually filled after the s of the following level, but that's not actually in all cases. So you can see here, this first number is which shell we're talking about, which ring. So the one here means this is the first ring. These are from the second ring. These are the third ring. But you see here goes 3s, 3p, 4s, then 3d, right? So this is again because the 3d is actually higher energy than the 4s. So the 4s actually gets filled up first before the 3d. Usually in many cases, but not in other cases. It varies again. This is something that you would have to kind of look at a case by case, but usually, and it's kind of safe if you really don't know, and it comes up on test day, which is kind of rare, but if it does, know that I think it's a safer bet to say that the 4s gets filled up before 3d. Okay, so that's again just like a general thing. But many of these you'll just have to memorize, or you'll have to understand them. Like luckily this is very low yield, and you very rarely will see these orbitals. They'll ask you to fill up these orbitals or say something about these orbitals. But in case they do, this is something, and it's even rare that they'll give you like a curveball. So, okay. Next up is Lewis dot structures. So for all atoms, the last filled shell is called the valence shell. So for example, we have here, we have this ring, which is the 1s ring, right? And you can see actually it only has 2 electrons because it's the 1s ring, which only has 2. Then this is the 2s, and then the 2p ring, I guess, as well. This says 2s, 2, and then has these 3 are for the p, going to the p orbital, right? And because this is the most outer ring, or the last ring, this is called the valence shell, right? And these 5 electrons would be the valence electrons, right? These are special compared to the other electrons because these are actually the electrons that are used for bonding usually. Many of you have likely learned Lewis dot structures, which specifically is a way to draw atoms to help visualize specifically the valence shell and the valence electrons, right? So if we want to look at nitrogen, which is right here, you can see its valence shell is 2 because there's 2s2 and 2p3, as actually 5. So it has 2 in the s shell and 3 in the p shell, right? Which is a total of 5 valence electrons. So you just write the element and then you do 1 nitrogen on this side, 1 atom on this, 1 electron on this side, 1 on this side, 1 on this side. So that's 4. Now you need to have a 5th one, so you can just put it anywhere because it doesn't really matter, right? Now this one is paired up. This is a pair. This has 1, so it's missing a pair. This has 1, so it's missing a pair. And this has 1, so it's missing a pair. Most of them will usually only have 4. Not always. Some have 6. Some can have 5 or 6 actually. Mainly like sulfur. Sulfur, fluorine can have, and we'll actually cover that a little bit later. But yeah, but most have these 4, right? They can have a pair, or they can only have 1 for the atom at least. Now let's do something a little more complicated. Let's do the Lewis dot structure for H2O, water, right? So we know that H has a valence electron, only has 1 valence electron. So these only have 1 dot. Oxygen has 6, so it has 1 dot here, 1 here, 1 here, 1 here. Then we double up here and here. So now this is missing its pair, this is paired, this is paired, this is missing 1, this is missing 1, and this is missing 1. Well, these don't really like to be missing one, so they want to fill their pair. So how would these two hydrogens fill their pair, and how would this oxygen fill its two pairs? Well, actually, what they can do is they can just join and join together like this, right? So this has one and this has one. So what are you doing? You each have one, and then you want to make two. Just share them. And what you're left with is this. So these are two it came with. This is hydrogen's one. This is oxygen's one. And this is this hydrogen's one and oxygen's other one, right? And now look, they're shared. And now everybody's perfectly paired up and everybody's happy. And this is the basic principle behind a bond. This is what a bond is, just essentially a sharing of electrons. And the way we draw that is actually like this. And then we can draw the two lone pairs. And that'll be the Lewis dot structure for H2O. And you can do similar steps for basically any compound, right? Any compound would have the same thing. Bonds, each bond represents, each line for a bond represents two electrons, right? A bonded pair. Okay. Now, let's find the geometric structure. Now that we know how to do Lewis structures very easily for compounds, it should be pretty easy to guess the geometric structure of most compounds. First, you have to see how many electron pairs the structure has. For example, H2O, as we just talked about, has 4. So it has, let's see, oxygen. Again, we'll just draw this like this, and dot, 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 right? So it has 4. Remember, this is 2, this is 1, this is 1, this is 1, and this is 1, so that's 4. Out of these, you have to see how many of these are lone pairs. Lone pairs are just these dots that are not bonded. So it has 2 lone pairs and then 2 bonded pairs. So I'll try BP and LP. Okay. And you just have to, I'll show you the table in the next slide, but usually you won't have a table, you actually have to memorize it, but for now, I'll show you the table and the diagram on the next slide. But you just match up the number of bonded pairs to the appropriate structure in your head. And so 4 pairs, going back to this, 4 pairs is a tetrahedral shape, which I'll draw here as the oxygen. Tetrahedral just means like this, essentially. Right, and this dotted line means it's going behind the screen, so it's like 3D, right? And tetrahedral, all of the lines are equally spaced from each other. So one is going up, one is going to each side, and then one's going up, one's going up, one's going to this side, one's going to this side. You can see here. One's going behind towards me, okay? And they're all equidistant from each other. So the angle between this one and this one is the same. Between this one and this one is the same. This one and this one in the back is the same. And then this one and this one in the back is the same, okay? And this one, the top one, and the one in the back is also the same, right? It's all the same angle, right? They're all equidistant. That's what tetrahedral means. But now we have to remember that we have this tetrahedral. I'll draw again here. But on this tetrahedral, this is a hydrogen, and this is a hydrogen. This is a lone pair, and this is a lone pair. We actually don't draw the lone pair, so we actually can cross this out. And this is also a lone pair, so we can just cross this out. And now all we're left with is this, right? You don't change anything. You keep it the exact same shape it was before. So you see how it had these lines? It was like kind of like bent. So you just keep it like that. And we can just redraw getting rid of the lines for the lone pairs. And this is the geometric shape of water, right? Notice how it's bent. A lot of people draw water like this. This is wrong. This is linear. There are molecules that are linear. For example, CO2 is linear. But water is not linear. Water is bent. Specifically, that's the name of the configuration, bent. Okay, and just to explain everything I've just been going over, just to show you, we have, like I said, linear. When you have 2, So this number on the left, this is how many total pairs it has, right? So for example, water had 4 pairs at the start. The 2 lone pairs and the 2 bonded pairs, that's 4 pairs. So we started off with this. When you start off with this, you start off with a tetrahedral. Once you start off with, and this is what it looks like. Remember, the dashed line goes towards you and this one's going back, right? They're all equidistant. Now, once you start off with 4, how many lone pairs is that? Well, if it has 1 lone pair, let's do this one at the top, doesn't matter, but let's do this one at the top. You can just cancel that out. Now you're left with just this. Well, what if there's 2 lone pairs? Now you have to cancel this one out. You have to cancel this other one out. And you're left with essentially just this, which is the bent configuration, and it's water. Right? If you have 4, but you only had 1 lone pair, so for example, they gave here NH3, you actually have a trigonal planar, trigonal pyramidal, right? So it looks like a pyramid. If you just connect these lines, it's a triangle base for a pyramid, and then it's coming up, right? So it makes triangular pyramid, right? If you have no lone pairs, you don't cancel anything out, you just have tetrahedral. If you start off with only 2, it's called linear. If you start off with 3, it's planar, and then you get rid of 1 and you get bent. So there's actually 2 ways to get bent. You can get bent this way, starting off with tetrahedral and eliminating 2, or starting off with a trigonal planar and getting rid of 1. Then if you have 5, which I mentioned, there's some elements that do, like here we have phosphorus, sulfur, bromine, chlorine. These can have 4. These have 5, 6 pairs. 5, 6 pairs, yeah. So if you have 5, you start off with a pyramid, right? This is just the same triangular base pyramid going up as it was before, but now you also have a pyramid going down, so it's a bipyramid. So it's pyramid both ways with a triangular base. You get rid of 1, and you're just left with a seesaw. Get rid of another, you're left with a T, right? Get rid of another, you're left with linear. Again, 2 ways to make linear. Octahedral, it's a square bipyramid, so it's a square base. Goes up, 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 and then down, 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 and then down. Essentially, square base and a pyramid up and a pyramid down. Get rid of 1, you're just left with essentially just a pyramid in one way, in one direction, which is up. There you go. And notice you just got rid of this and all the connecting lines. And then square planar, you get rid of this as well, and then you're just left with a square, right? Very simple. This you have to memorize. There's not really any way around it. You just have to memorize it, but it's not that complicated. I think at least just to memorize this, not compared to some of the other stuff that you have to memorize for biochemistry especially. So I think this shouldn't be too bad, hopefully. And looking at a diagram really does help. Another thing that you should memorize for each geometry is also the bond angles that it makes. So for example, obviously for linear, it's not that complicated. If you have just a straight line, the angles between them is just 180 degrees because it's a straight line. If you have just a triangular plane, 120, 120, 120, it makes 360. If you have a bent, it's 118. This one's really important, tetrahedral. Tetrahedrals are actually very common in molecular geometry because a lot of carbon bonds, especially for organic chemistry, biochemistry, a lot of carbon bonds are tetrahedral. So tetrahedral, especially in the body, is found a lot in organic chemistry and biochemistry. So yeah, and the angle is 109.5 degrees between these, this, right? The angle between each of them is 109.5. For the trigonal bipyramid, it's between the bottom and the top and any of the sides. So these guys, it's 90 degrees, and same thing for the bottom, it's 90 degrees, right? Because it's you can see here there's right angles. Right angle right here, right angle right here. Okay, and you have to think of it a little bit in 3D, so it's hard to see, but yeah. But it's also at its core a triangular base, so the angle between this and this is just like in the planar is 120. Right here and right here. Okay. Octahedral, 90 degree in all directions. 90 degree like this from the bottom and the sides, and also the sides, it's a square, so it's just 90s between them. Okay, very simple. And square pyramid is obviously the same thing. Square, planar, T-shape, linear, those are very easy to figure out. Okay. So I recommend memorizing some of these as well. Okay. Well, now let's do a clicker question. What are the bond angles in iron 3 acetyl acetonate? And this is a very, I would say, realistic question that you might see accompanying a passage. Obviously, you don't know what iron 3 acetonate looks like. I don't either. But since it's accompanying a passage, in the passage, usually in a figure, they'll actually show you what it looks like, and I've included it here. So this is something that they might show you. It's just an iron, which they know is iron 3, right? And 6 oxygen things, right? And they're just going to ask you to find what the angle between them is. Okay, so I'll give you guys a couple of seconds. Okay. So what again, what are the bonds? Sorry, I have to fix my recording. Okay, give you guys 30 seconds, and so the correct answer is only 90, and let's talk about why that is. So as you can see here, iron has 1, 2, 3, 4, 5, 6 bonds to this oxygen. Therefore, we can just draw it in 3D structure. You can skip the Lewis dot structure because we don't really need to, because it's already shown here that it has 6 bonds. So essentially, it's kind of like a Lewis dot structure. And remember, 6 bonds looks like this. And I'll just write each of these as an O. Right, and then if you connect these, this is a square pyramid. Sorry, it looks kind of bad, but just pretend. It's a square bipyramid. I think it's called an octahedral. And there are no lone pairs because it has 6 bonds. So really easily, you can just see either through your own memorization of what an octahedral has, which is only 90-degree angles, or you can actually just see it 90-degree, 90-degree. All of these are 90 degrees. Right here, right here, right here. All of these are 90 degrees between every bond angle. Okay. Okay, and that just gives you 90 degrees, right? So really, that question was actually very simple if you just really knew what to do, which was, okay, I have to know the geometry. What is the geometry? Okay, well, it's not octahedral because it has 6 bonds, right? You go back to this. If it has 6 bonds, so static number 6, it must be an octahedral. Okay, how many lone pairs does it have? Okay, no, it has no lone pairs because they're all bonded. So it must be an octahedral, must stay an octahedral. So octahedral now has all 90-degree angles, and that's it. That's the answer. Okay. Very easy, very simple. Okay, moving on to bonding. So basic bond types, there are 4 basic bond types that we'll be looking at. There's ionic bonding between metals and nonmetals, covalent polar bonding between nonmetals with a significant electronegativity difference, covalent nonpolar bonds between nonmetals with an insignificant electronegativity difference, and metallic between metals. We're not really covering metallic bonding that much because it pretty much never shows up, but I just wanted to mention it's one of the types of basic types of bonds, but the first 3 are really what we're covering. Okay, the most important difference, polar versus nonpolar. Each atom has a certain electronegativity, or you can think of it as a desire to pull electrons from its bond partner. Remember when we were talking about H2O, the hydrogen and the oxygen. They each have 1 electron in their valence shell. They want to both fill it. So they decide to come to a mutual understanding and share them. But sharing is not always completely equal. So some things can be shared by one party more than another. For example, if you and a friend decided to share a car together, and they decided that they need the car 5 days a week and you only needed 2 days a week, so they get the car 5 days and you only get 2 days. You're still sharing the car, but it's unequal sharing. It's not like you're both sharing it the same number of days. Okay, that's exactly what it is with electrons as well. And the way this is determined is by something called electronegativity. So the higher the electronegativity, the more the atom or molecule wants to pull electrons towards itself. Non-metals have a much larger electronegativity than metals, and so in ionic bonds, because the electronegativity is so big, it's actually not even a sharing really at that point anymore. It's always a stealing, where the non-metal like fluorine or oxygen or whatever steals the electrons from the metal, like for example sodium. So if you had NaCl, which is salt, the chlorine steals the electrons from the sodium, right? It's not as much sharing as it is just you taking. In covalent bonding, though, between two non-metals, it's instead more of a sharing than it is a stealing. However, sometimes one atom still has a higher electronegativity than the other, resulting in an unequal sharing, right? And this is what we call polar bonding, because it has poles, right? Like if you think of the poles on a magnet, a positive and a negative end, right? The opposite of this is a perfect or near perfect sharing between molecules. That happens when they both have the same desire. So for example, if I desire the car, going back to my example, I desire the car for 1 week and you desire it for 1 full week, and we both decide every other week we'll get the car. So it's an equal sharing, right? That's what happens when we both have like an equal desire versus where I needed for 5 days and you need 2 days. It's an unequal sharing. The most common examples of equal electronegativity between two of the same atom. For example, oxygen, is found as diatomic. It's usually in nature in the air found as O2, and it's just two oxygen molecules bonded together. And so, because oxygen has the same electronegativity as oxygen, so it must be equal sharing, right? It must be non-polar, right? And that's true for anything: nitrogen, N2, O2, Cl2, whatever. Or between carbon-carbon bonds, which is also very common in organic chemistry. Another thing that's common in organic chemistry is carbon-hydrogen bonds. Carbon and hydrogen also have essentially, it's not perfect, but it's near perfect electronegativity. So carbon-hydrogen bonds are also considered nonpolar, and that's why you may know from organic chemistry, usually things that are hydrocarbon heavy are considered nonpolar molecules, right? This is because they have no polar bonds in them, right? And conversely, if you had a carbon-oxygen bond, like for example, an alcohol or something like that, that's considered polar because it has a polar bond. Okay. So in a polar bond, while the difference is not large enough to create a full positive or negative charge, like in ionic bonds, like NaCl, you have a full positive and a full negative. The Cl is fully negative. The sodium is fully positive. The difference in electronegativity is enough to create a partial positive and a partial negative, and which is denoted using this symbol, this Greek symbol. It also creates something known as a dipole moment, which has a magnitude and direction. So this is going back to physics. If you remember, like force vectors, this is essentially a vector. It has a magnitude and direction. The direction is always from the positive to the negative. And again, as with forces, they use vector addition because they are vectors to determine net moment. So for example, if you had two equal but opposite forces, they would cancel out and you would actually have no force on an object. If you had two equal but opposite dipole moments, they would cancel out and there would be no net dipole moment. Like for example, you see here in CO2, there's a moment from this carbon. Remember, carbon is much less electronegative than oxygen. So this is the positive end, this is the negative end. This one goes this way, this one goes this way, equal direction, opposite direction, equal magnitude, sorry, they cancel out, so there's no moment. Whereas with water, it goes from the hydrogen to the oxygen, so it goes this way and this way. The left and right cancel out, so it's just up plus up, which is just like really up, I guess. There's just a lot up, and that's the net dipole moment is just up. Okay. And if you're confused a little bit on that, I recommend going to watch like a physics lecture on like forces and vector addition with forces, and that should clear it up for you. It's exactly the same. The electronegativity trend based on the periodic table is this way. The positivity goes to the right this way, and then decrease in this way, right? If you look at this, that means fluorine is the highest, and it is with 4.0. Oxygen is the second highest with 3.5. So basically, if you see fluorine Here, they'll always have a partial negative end. So if you see oxygen or fluorine bonded with anything else, they'll be the negative ones, right? And you can see here, hydrogen is kind of close to carbon. It's a little bit different, but you really don't have it's not enough to make a polar difference, okay? Whereas carbon and oxygen is to make enough, carbon and Cl, carbon and nitrogen, whatever. Okay, next let's talk about double and triple bonding. So in addition to the standard single bonds, compounds can have double or triple bonds. These additional bonds are called pi bonds in contrast to the first sigma bond. So if you look at this, which I'm the orbital overlap, which I'm not covering really in depth because it's not very high yield, and you can learn it on your own if you want to, and if you want to be safe, then you can. And I'm sure you've learned it in general chemistry before, probably in organic chemistry. You can see here there's this sigma bond, which is this overlap right here between the two carbons, and this is the single bond. This one's really strong, very hard to break. But there's also these p orbitals, which create these pi bonds between these two carbon molecules. These are much weaker. You can have double and triple bonds, but they're usually weaker than the first one. Sorry. Again, they're easier to break. And that's an important reason why fundamental organic chemistry reactions like addition reactions are allowed to happen, because it's much easier to break double bond than it is to break a single bond. Okay. And I went over that quickly because I don't think it's extremely important, but yeah. Another unique feature about pi bonds is that in many compounds, they're actually not entirely present. So even if it may appear they are, there are actually resonance structures for these compounds, meaning that within any time frame, all of the possible resonance forms exist and are constantly fluctuating. So for example, like the easiest example is if you had a double bond right here between this carbon and this oxygen, and you have these other ones. Actually, it doesn't exist like this. It exists as this as well, and this. All three of these with the oxygen different ones, the bond different ones existing at the same time. And it's constantly fluctuating, constantly changing. They all exist at the same time. And so what actually happens is it's not a full bond with anything, but it's more like a partial double bond with all three of them. And this can happen in this situation. And some of you may remember if you draw a benzene ring like this, but you can also draw a benzene ring like this. Let me see if I can mix it up. Yeah, like that, right? Both of these are correct. So most of the time we end up drawing benzene rings like this, right? This just goes to show that all of these bonds, like there's double bonds everywhere and they all have double bond characters. So double bond can really be anywhere, right? So that's why I draw a circle inside. And for this reason, okay? And all the bonds have partial double bond character, okay? Note that some resonance forms are more stable than others. Like for example, here, these are all the same, right? Because they're just flipped. So they're all equal, but in other things, there's ones that are more favorable, more unfavorable. They all exist, but some exist more, I guess, than others. It's a fundamental principle of organic chemistry. And so again, the reason why a lot of reactions in Cs are able to proceed. Okay. Okay, next, another important aspect of double bonds is their ability to have E and Z configurations. This is because there's free rotation around a single bond due to its flexibility, but there is not free rotation around a double bond as it's more rigid. So, whereas if you had something like this, this can really be the same as this. Because around single bonds like this, you can just have free rotation. So this can be, these can actually just be rotating and like flipping and moving around, and you can move the CL up, you can move it down. On either side, you can move it any way you want, because around a single bond, there's free rotation. It's very flexible. But as soon as you have something like this, where it's a double bond right here in the middle, okay, suddenly you cannot have this rotation anymore because double bonds are rigid. They're much stronger and they're much more rigid than single bonds. So you can no longer have this rotation. Thus, this and this are no longer equal, right? They're now completely different. Whereas in single bonds, they're essentially the same because if you just rotate it a little bit, it's the same thing. Okay. And so we have names for one version versus another version, right? These are essentially the same thing, but these have different names. And you can see right here, so these look very similar, but one of them is the Z and one of them is the E. The way to determine whether it's E to Z is by determining the priority of the four groups on both sides of the bond, right? So you have the double bond right here, right? So you have to determine the priority of the groups on both sides. So what's the priority of this? It's 1 versus this one, 2. What's the priority of this one? 1 and 2, right? Because this has higher priority than this. So this is 1, this is 2. This has higher priority than this. So this is 1, this is 2, right? Okay. And then determine if the highest priority groups on both sides are on the same side, Z, or on opposite sides, E. Like for example, if you look on here, you have the double bond. This is priority 1, priority 2, but this is priority 1, priority 2. So these are on 1 and 1 are on the same side, 2 and 2 are on the same side. This is they're on opposite sides. One's above, one's below. And an easy way I learned in organic chemistry to remember this, and that kind of stuck with me, is if they're on the same side. So same, but with a Z, like same side is Z, right? And then E is the other one. So same side is Z, same side, like that, and then E is on opposite sides. Okay. Talking about priority, so molecules like fluorine, chlorine, bromine have the highest priority, followed by things like nitrogen, and then carbon compounds like CH3, which is what it is in this case, and then lastly, lone hydrogens are the lowest priority. So for example, if you had a CH3 on this side and a chlorine right here on this double bond, then you had hydrogen and CH3. Even though the CH3s are on the same side and you would think this is Z, it's actually E, because this is priority 1, priority 2, this priority 2, priority 1. So they're on opposite sides, so it's E. Okay, and you just have to remember that, right? And it's the same configuration, the same order priority as it is with RNS configuration, right? Which some of you may know. Okay, so another measure of the strength of a bond is its length. It's important to remember that bond length and bond strength are inversely proportional, meaning if a bond is really long, it's weak. If a bond is really short, it's strong. Okay, we can logically conclude that double and triple bonds are stronger than single bonds, right? Obviously, having to break 3 bonds, even though the pi bonds are weaker than the sigma bond, you basically have to break the sigma bond and then a pi bond and then another pi bond versus just a sigma bond, right? So double and triple bonds are stronger. Thus, they're also shorter than single bonds. So double and triple bonds are much shorter than single bonds. And the thing is, the larger a molecule is, the longer the bond it forms, and thus the weaker. For example, hydrogen with bromine, HBr, bonds are longer and weaker than HCl bonds due to bromine being longer than chlorine, right? And the way you know that that bromine is larger than chlorine is by going to the periodic table. And again, remembering by size, I'll actually just write here. So things like going down get bigger, going down gets bigger. And then also going left is also bigger. So down left is the biggest, right? And the reason for that, so let's talk about why going down is bigger, right? So fluorine has a number of, I believe, 9. So it means it has 9 electrons. which means as the 1 shell and then the 2 shell. Chlorine, I don't remember how many chlorine has, what chlorine's number is, but let's say it's whatever, 14, 15, 17, whatever. It would have more electrons, thus it would have another shell. Bromine would have another shell. Iodine would have another shell, right? And you can see how each time I'm going down, more shells get added, so the molecule gets bigger, 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 bigger as it has more shells. Okay? So obviously things get bigger as you go down because you're just adding more shells because more electrons. As for why going left is bigger, gets you bigger, is because fluorine also go the same thing, it has 2 shells. Then you go left to oxygen, nitrogen, carbon, boron, you still have the same 2 shells, right? So fluorine and oxygen have the same number of shells, so they essentially are the same size, but fluorine actually has more protons in the middle, right? Having more protons because it's a higher number. So having more protons means that the protons and the electrons obviously attract, right? Positive and negative attract. So protons in the middle are actually attracting the electrons to themselves. More protons actually means a stronger attraction. Essentially, it's like if you had like a ring and then you just pulled it inward, it would kind of get like compressed a little bit. The compression on fluorine is more than the compression on oxygen, which is more than the compression on nitrogen, which is more than the compression on carbon, right? Even though they have the same number of rings, valence shells, having more protons makes you actually smaller because it compresses you by attracting you more. Okay, that's why going down left is bigger usually, unless you go like down a shell, in which case you're not, but that doesn't happen, right? Okay, so that's it for the lecture for today, and thank you guys for joining. Here's my email if you need it. Hopefully, please send me any questions or anything, comments, concerns, anything like that that you want to send, and I'd be happy to answer either via email or via meeting. Okay. Thank you very much.